Hello, this is Minsu from Quilt, and I'm going to introduce our research, Quilt, a robust data segment selection framework against concept drift. Robust AI is becoming important, especially in continual learning, which is common in industrial settings where models need to be periodically trained on data streams. As shown in the visualizations of data, the applications include manufacturing, meteorology, and finance, and it is natural that these data distributions can shift or change over time. Regarding distribution shifts, the joint distribution of data with feature X and label Y can be decomposed into two parts, with a prior distribution and a posterior distribution. So there are three sources of distribution shifts, where only one of them drifts or both drift. Most existing works about distribution shifts actually focus on the virtual drift problem, where only the data distribution changes and not the decision boundary. In this work, we focus on actual drift or concept drift problems, where the decision boundary can drift significantly. Concept drift means that statistical properties of a target domain changes over time, and it is formally defined as a change of joint probability. So, if a concept drift occurs, it implies that the current distribution changes from the past. And here is a simple synthetic concept drift dataset called SIGN, which shows distribution changes severely over time, where blue dots are with class 0 and red dots with class 1. The problem of concept drift is that it leads to decision boundary shifts, so previously trained models cannot predict well on the new data. To handle this concept drift problem, there are two major aspects of concept drift research. The first one is concept drift detection, to identify change points or change time intervals. These techniques use change of data distribution or model performance for detection. And the next one is concept drift adaptation, to update existing models according to the drift. Most adaptation techniques are based on model-centric approaches, where the historical drifted data is either discarded or replaced with trained models. And they focus on updating the model with new data or taking an ensemble of previous models. However, we contend that taking a data-centric approach of selecting previous data segments to train a model can be a more fundamental solution. So we propose a data-centric framework called Quilt that retains previous data that is still useful for training. And the overview of Quilt is shown in the figure. We can divide the framework into two parts. The first part is data segmentation. Since individual sample selection is inefficient, we first group samples that have the same concept into data segments by applying existing concept drift detection methods. For data segmentation, we use the idea that data within the time interval between consecutive drift points has the same concept. So if we split data into segments using detected drift points, then each segment represents a concept and becomes the unit of data segment selection. If a drift occurs, we train a new model jointly combined with data segment selection method, which is the second part of the framework. And there are two goals while selecting data segments. First, we should discard data segments that represent drifted concepts compared to the current one, because using them for training reduces model performance on the current concept. Second, if there exists similar or same concepts of data segments in the past, we want to select a core subset of non-drifted segments for training efficiency, but without compromising accuracy. To achieve both goals in a holistic way, we propose gradient-based disparity and gain scores that is used for discarding data segments with concept drift and selecting a minimal subset of segments without concept drift, respectively. We first define G as the gradient vector of the data and Y as the label of the data. The disparity score is defined as the L2 norm distance between two averaged gradient vectors of a training subset and the validation set. And the gain score is defined as the inner product of the two averaged gradient vectors. We also provide a theoretical justification on why the disparity score captures concept drift. For analysis purposes, we make the simplifying assumption that the prior distributions of the training and validation sets are the same, although their labels are different. Our theorem shows that the disparity score is upper bounded by the expected amount of label change, which is the concept drift in this setting. More details can be found in our paper. So, we use the disparity score as a proxy to capture concept drifts and discard drifted data segments. Next, we analyze the behavior of disparity and gain scores with a simple setup where there are only two concepts of data segments with the same prior distributions. We generate a synthetic dataset for two cases where there is no concept drift or there is a concept drift between the two segments. And we monitor the disparity and gain scores while running Quilt and observe following trends. In this setting, disparity and gain scores help select desirable data segments for selection which have low disparity and positive gain scores. In case 1 with no concept drift, which is our desirable segment, the simulation results show that the disparity score is low, close to 0, and the gain score is positive. However, for case 2 with a concept drift, which is our undesirable segment, the results show opposite trend, that the disparity score is high compared to non-drift case and the gain score is negative. We can also find out the gain value converges to 0 for both cases as a converged model has nothing to further gain, but the disparity value does not, as it indicates drift severity. And next, we show how to select data segments using both scores and jointly combine the data segment selection component with model training. In the algorithm line number 9, our algorithm selects data segments depending on two gradient-based criteria which have positive gain scores and low disparity scores. It then updates the model with selected data segments, and this process is repeated for every epoch during training. So, as the model training proceeds, the selected data segments can change according to the current model state. In the experiments, we demonstrate the following two perspectives of experimental results and analysis. We evaluate Quilt on 4 synthetic and 5 real datasets. We compare Quilt with 4 types of baselines, which are naive methods, model-centric methods, data-centric method, and data subset selection methods. And we use simple neural network classifier as a base model for our proposed method, Quilt. We first compare Quilt with the other baselines for accuracy and runtime, as shown in the table. The results for other 3 datasets are similar and shown in our paper. Overall, Quilt outperforms all the baselines in terms of accuracy because it effectively utilizes the drifted data, but also efficient in runtime using core subsets. We next verify whether our data segment selection algorithm actually finds core data segments and discards drifted data segments. To evaluate our data segment selection, we construct a gold standard solution by performing an exhaustive evaluation, where we evaluate all possible combinations of data segments and choose the one that results in the highest accuracy on the validation set. We refer to this exhaustive searching method as best segment. We then measure the precision and recall of Quilt selection results against the best segment solution, as shown in the table. The higher average recall and precision values suggest that Quilt selects almost all of the useful data segments, and also some more similar data segments as well. The accumulative model evaluation results shown in the figure also indicate that Quilt shows competitive results with best segment, so we actually achieve most of the room for improvement compared to optimal solutions. More results for other datasets are similar and can be found in our paper. In this work, we proposed Quilt, a data segment selection framework that is robust against concept drifts. And Quilt employs an effective and efficient data subset selection algorithm that holistically discards data segments with concept drifts using the disparity score, and also select core data segments using the gain score. Our experiments on synthetic and real datasets show that Quilt achieves state-of-the-art accuracy against concept drifts and is efficient. Thank you.